All right, let's start. All right, let's start the second part of quantization. Right. So in this lecture, we are going to keep talk about this linear quantization. We're going to talk about some following operations, and then we are going to wrap up with binary and ternary quantization, as well as the mixed precision quantization. Right. So well, linear quantization. So far, I'm just going to this is a review process. So we have this. So we have, we established that for a matrix operation, matrix multiplication, or a convolution operation, we already established that linear quantization can help us to reduce the storage, reduce the computation, right? But those are only for two particular operations. Next, what I want to talk about is this there are three parts. This post-training quantization. So the first part is that, well, like a whole network has, different layers, right? You have a fully connected layer, you have quantization layer, you have different channels, you have different kernels, you have all these different inputs and outputs. The first question is, that linear quantization, what kind of a granularity we should use? Should we do this for a whole layer? The whole layer using the same quantization. Because remember, when we are doing linear quantization, we need to decide the S and the Z value, right? Should we do, this whole thing for the whole layer, or should we just do that for a particular channel and each channel do it differently? Or we should do just, a small factor. So this the first thing we want to determine is this quantization granularity, okay? The second thing is this dynamic range for both the input and the weight. I think I forgot. Shogun, did you ask the question like for inputs, they change, right? The inputs keep changing, and how do we determine the range for the input? Okay, so that's another question we want to answer. So and finally, once we determine the quantization, all these the bits, the quantization bits, and all that, like all these centroids. How do we round the actual number to the centroids, to the numbers? Okay, so those are three questions we're going to answer for linear quantization. Okay, so let's first start with like this granularity, like, where shall we apply this linear quantization to? Should we apply to this whole tensor, or this whole layer, or just a channel, or just a small part? Which granularity gives you the best overall result? That's the question we want to answer. So first, let's see. And remember, this quantization can be applied for both the weight and the activation, right? So those are we're going to talk about both. Excuse me for that, but I'm going to, you don't need to read that. Let's just look at this chart over here. What this chart shows is like the x-axis shows the output channel index. So basically for this particular layer, I have multiple kernel, right? For this convolutional network, I have multiple kernel. And for each kernel, I have corresponding to one output channel. So that's good, right? And if you look at the channel output, and we just, and we list all of them. So the x-axis is the output channel indices, okay? And for each particular output channel, for example, like the green channel, the yellow channel, and the blue channel. For each, let's say like the green channel, and if I list all the values of that particular channel, you will see, this range, okay? And for the yellow channel, you might see this small range. Okay. And then for the blue channel, you might see another, range. But what is this, this kind of like candlestick? What is all this, wick and all this, what is this body? So like that kind of shows you what's the majority of the value, like it's concentrating. For example, like for this layer 20, I'm sorry, channel 28, like the majority of the value actually is concentrated in this small range, and the others are just outliers. Make sense? So what the takeaway from this is that all these output channels, they all have, and all these data range have different characteristics. They have different range, they have different distribution. So that's the takeaway. And then like if let's say like I want to do the linear transformation, the linear quantization for the whole tensor, for the whole layer, means that I need to calculate the range for everything together and to determine the 0 point and the scale. Does that make sense? And that doesn't work very well for the accuracy. Okay. I thought if I have a data. Okay, this is an example. Yes, I use this example. So end up like, that doesn't work very well. Let me show you the example here. So here, this divider here on the right-hand side, this is the whole tensor quantization. Means that we go to do the profiling, we get the quantization for the whole, all these output channels. Make sense? And if you look at this, for this everything together, you can see what is the maximum. I'm sorry. So for this whole, let's say this whole tensor, the maximum is 2.12, right? And the Q maximum, how many bits are we using here? We are using 2 bits. Okay. So the scale is 2.12. Okay. And if we do this for this whole tensor, what do we end up of the quantization is this? Okay. And then like, I think we are assuming the 0 is the 0 point is 0. Okay. So if we do this, and if you reconstruct the matrix, you got this. Okay, compared with the original one. So how's it? And this quantization error, this reconstruction quantization error is 2.28. Okay. And if we are not doing for the whole matrix, for this whole tensor, we just do, this quantization for each separate channel separately. Let's see what's happening. Okay. So let's see. If you just do the quantization for each particular channel. For the first channel, the largest number is 0.9. Again, the quantization is 2 bits, so the scale is this. For the second row is this. Third row is this. Fourth row, so each channel has its own quantization. And anyways, by doing this, we have multiple scale, multiple 0 points, but the reconstruction gives you this matrix, and you calculate the reconstruction quantization error. The error is 2.08, which is smaller than this 2.28, and that agrees with if you do some experiments with a larger network. I thought if I have data to show you the comparison of potential quantization versus per channel quantization. Okay, but that's the takeaway is that per channel gives you more control, finer granularity, give you less quantization error. Okay, good. So even with the mess up text, I hope the idea is clear, right? Other than potential quantization and the channel quantization, they also have group quantization. For example, I just set a small group of just a small vector and only quantize that vector instead of the whole channel. Yes.
still a question. So is the pre-channel optimization slower than the pretensor optimization? Yes, you use like one way to represent the whole channel, and the other one just use like one way to represent the whole tensor.
Well, first of all, like you're not using the whole weight, right? You're using one scale factor and one 0 point for the whole tensor, and you have scale and the 0 point for every channel. Slower in terms of, well, there are two things, right? So one is when you are doing the quantization, it's a little bit slower because you need to calculate more, but that's a one-time thing. Okay. But during the inference, it doesn't matter because you're all doing this x and the 0 point, but you're just using different values, right? So during the inference, during the runtime, it doesn't matter. During the quantization, offline quantization, you pay one-time fee. It's a little bit higher one-time fee.
Yeah, makes sense. Thank you.
And then like also like if you, so it's again, it's about trade-off, right? So if you have a finer granularity, then you have more quantization to do, but that gives you a finer quantization. Because if you think about it, if you push this to the other extreme, you do quantization for each individual number. That's essentially itself, right? So that's kind of where the trade-off is. So then we can also do per vector quantization. Or some of them, they have this shear macro exponent data type. What that means is that for a vector, like the whole vector, the values share the same exponent. Does that make sense? So that you can save the storage. This one basically says like this vector group quantization works and has this hardware support. In this NVIDIA GPU, this Blackwell GPU, they support this group quantization and can provide throughput theoretically 2 times higher throughput improvement compared to the floating point 8 and the floating point 6. What is this? So other than that, you can also do this nested hierarchical scaling factor. That probably will also like answer part of your question. What happens is that, well, first, I'm going to have a scaling factor for the whole tensor. So that's one level. I have an S and SA 0 for the whole tensor. And that number usually is this number, this gamma number usually is a floating point number. After you do the scale, then like, you got a new matrix, right? And within that new matrix, again, we are doing a group vector level linear transformation. Then you got another scale and another 0 point. Does that make sense? So by doing this 2-level quantization, the benefit is that, well, then like on one hand, you keep reducing the storage, right? But why we are doing this, why we are doing this for the internal scaling factor, usually it's an integer, and for the external scaling factor, usually it's a floating point y, because usually for the calculation to get the final result, we need to use the gamma, right? But there are, when during the matrix multiplication, there are a lot of small internal calculations. And for that one, we are setting the scaling factor to integer, so the internal numerous calculations do not need to be involved with this gamma. So it can be faster than storage for this internal nest. Does that make sense? That's just a optimization. So the details is in this VX Quant paper. And apparently their results suggest that this way you can improve both the storage and the computation. And it's about the trade-off between the accuracy, the storage, and the computation efficiency. Okay. So that kind of answers like, where do we apply this linear quantization to, right? So next question, like, how do we determine the dynamic range? Um, you know, um, Unlike the weights, the activation range varies across inputs. That's exactly what Shogun asked. To determine the floating point range, the activation statistics are gathered before deploying the model. Okay. There are multiple different ways to do the statistics and to determine the range. When we are determining the quantization range, essentially we are determining, say, oh, I have this weight distribution, and I have these so many bits I can use to quantize this whole range, right? Where should I concentrate to, right? Means that like, well, out of all these whole value distribution, apparently with limited number of bits, I cannot capture everything, right? Because that's the whole point of quantization. Then the point is, where should I spend my limited number of bits to the most valuable input data, right? So that's the determine the range that I want to apply to. There are a couple of different ways to determine the range. One way is that you kind of calculate the distance, the range during the training stage. So you have a moving average, exponential moving average, and then you kind of like gradually calculate it while you are training the model. Because when you are doing the training model, you have all these training data coming into your to your input to your model, right? But remember, the training data, they are not necessarily exactly the same as your testing data or your future data, right? It's just like, the best guess. While you assume that, the data you see in the future, they are pretty much will follow the similar distribution as your training data. So that's the assumption here. So you are calculating, if you are familiar with exponential moving average EMA, what is essentially you have this alpha times this R, the range, plus this 1 minus alpha. Alpha is the hyperparameter times the R from the previous iteration. Okay, so that's kind of the dynamically calculating the maximum number, minimum number for the input. Does that make sense? There's a second type. It's more the second type of statistics is this. So instead of like I do this statistic during the training stage, I do this during the inference stage. So during the inference, I'm going to run a few batch of this so-called calibration batches, and I assume the future data I see is going to be similar to the calibration data set. So after doing this, running this calibration batches, I'm going to use the mean of the min max of each sample in the batch, okay, and calculate the range. And there are a couple of different methods to determine the range. So the first method is to minimize the mean square error between the input x and the reconstructed quantized input qx. Okay, so this equation, this is the objective we want. We want to minimize the mean square error between this quantized error and the quantized input and the real input. So for example, if you look at this figure over here, this is the whole input, data distribution. Okay, so this is the input distribution. the minimum can be here, this here, but we only have a limited number of bits to use for these inputs, right? So now, but essentially, what we want to determine is that how do we move this range to capture the majority of the input data? Does that make sense? Because, for example, well, for a fixed number of bits, the range that it can capture is fixed. Basically, all these blue dots, they are pretty much fixed, right? We only have so many blue dots. Make sense? But let's say like, if I want to map the blue dots on the very end over here, so I end up using the blue dots for some of these outlier numbers, which are probably not so significant. And for some of these, inputs that I don't have, they are out of my range, and I did not capture all those values. Does that make sense? If that's the case, it's not a good map, right? So you are trying to map this input data range to the fixed number of blue dots. Okay. And if we knew the input data distribution, let's say like a Gaussian distribution, okay, or a Laplace distribution. If we knew the distribution of the data and we knew how many bits we have, you can numerically calculate what is the optimal mapping here. Okay, so that's that. Another way, and this is to minimize the mean square error. Another way to how to decide which bits I need to use for what input is to minimize the loss of information. So these two are similar but different things. So for the minimum mean square error, what we are trying to do is that the quantized data, they should follow the shape of the original distribution, right? Right. But to minimize the loss of information, is that it's not that we want to exactly match the shape. The meaning is that we want the integer model encodes the same information as the original floating point number. The information and the shape, they are two different things. Okay. And the loss of information can be measured by this KL divergence, which is a metric to evaluate how close two distributions are. Okay, I hope you. So KL divergence measures the amount of information lost when approximation is when approximating a given encoding. So basically, as it says, is that when I'm approximating a distribution with a new distribution and how close they are, how much information I lost when I'm doing this approximation. So that's the loss is what we are trying to minimize. Does that make sense? And they have a different calculation method. Oh, the equation was given here. I'm going to fix the equation and re-upload the slides. And this one gives you this visual explanation. So if you want to minimize the KL divergence, so what I end up is like, let's say like in this figure, the x-axis is showing all these different activation values. The y-axis shows the number of counts. Okay, and if you want to minimize the KL loss, we end up deciding the cutoff line is so only all those blue dots like before the cutoff line will be used, will be quantized, and the rest of them will be just discarded. Does that make sense? So, for example, like for any number, so you can see that, let's say like this number probably is 60. No, I'm sorry, probably is 40. Okay. So let's say like well, I have 0, 1, 2, 3, 4, all the way to the 40. And that's the number of counts, right? So I decided to use all my digits, all these quantization, all these bits to represent all those bits less than 40. Then now in the input, what if I have the 300 value? What do? Right? I just, but the maximum number I have is 40. I would just use 40 to approximate this 300. Does that make sense? So in this way, the input now is just approximated. But the KL divergence basically dictates that, well, by doing that, even doing that, you are using a number 40 to approximate these 300 and 400 because like there are number of counts are very little, very small, and this one will give you the minimum loss in terms of the distribution of the information. Does that make sense? Okay, so that's that. So we end up using the KL divergence, we end up deciding the cut lines here. Everything larger than this, I'm just going to use 40 to represent, and everything else has its own number. Okay. Okay, all good. This one shows, for AlexNet, for ResNet, and they show, they have different cut lines for when you are trying to use the KL divergence to calculate where should you cut it. Another method is the so-called like this clip to quantization. So basically, is that I want to determine for certain distribution, I want to determine where the clip is. It's very similar to KL divergence in terms of the goal. You basically want to determine that. It's also like trying to minimize. So I don't think I have the details of this method, but the main idea is also like basically you want to try to determine where you want to clip this original distribution, and then you want after you do the clipping, the new quantized data and the original distribution is also trying to minimize the mean square error. Okay, and they use an algorithm called octo-apps to iteratively find the where the clipping point are to minimize the mean square error. So after you do, after you determine, all these the quantization bits, essentially you determine all the grids, right? All this where the grids are. So remember in signal processing class, when you already, let's say like this is the original signal, and you already determine all these quantization bits and where the grids are. In signal processing, like when you are trying to round the number to the quantization, usually we are doing what? Are we always doing up rounding, low rounding, just rounding? Anyone remember? Well, naturally we were saying just do a normal rounding, right? So if it's a greater than, let's say like if it's greater than 0.5, it's going up. If it's less than 0.5, we go to the floor, right? So if it's greater than 0.5, go to the ceiling. If it's less than 0.5, to going to the floor. That's the natural way to do the rounding, right? Right. So, and you may think, in this case, like, well, can we just do the same? And that's at the beginning, like we just do that. We just do the rounding up and down, depending on the value of it. But it turns out this rounding method isn't the optimal method in terms of the network accuracy. Because remember, when we are doing the rounding, we are kind of trying to minimize the quantization error. So if you do the quantization, the rounding to the nearest, for example, for 0.3, if you round to the nearest, this one should go to the ceiling, right? So go to the floor. So it should be 0. And 0.5 should go to 1, 0.7 should go to 1, 0.3 should go to 0. Does that make sense? So that's minimize the quantization error. But people find out that's actually not the optimal in terms of the accuracy. Why? So what we really want is the rounding that can reconstruct original activation, because that's the thing we want. We really care, right? Does that make sense? So we don't care about the rounding error. We actually care about we regain the original activation value, right? So that's the key observation here. So and that rounding, the rounding that gives you the original activation actually is not the same as rounding to the nearest. Okay. So that's the key takeaway. So they essentially this equation that's I want you to find you know the mapping that give you the that's to reconstruct the activations. And there's this paper called this ADA rounding. I think it's this paper. This ADA rounding, the adaptive rounding paper. What it says basically says what they did is instead of always rounding to the nearest, we want to choose from this floor and the ceiling to get the best reconstruction. And the paper proposed a learning-based method to find the quantization value for the original W. And how it's framing it is this. So the W tilde equals to the floor of W. Let's say like if we have 1.5, then you are going to have a 1 here, plus a delta. And delta is within like 0 to 1, and then to route to the nearest. And they are trying to optimize this this equation here. If you what it says is like this Wx minus this W tilde. So that's the mean square error of the reconstruction, right? So this is the original input. This is quantized input. And they have a regularization term to enforce. This regularization term is trying to force you to take the 0 and 1. So by optimizing this equation, you can find the rounding that gives you the best reconstruction capability instead of like to the nearest. So it's a whole paper. I can just give you this as a very high level idea here. If you are interested in like the math and the algorithm, you can check out this paper. So far for linear quantization, we talked about the scaling factor, the 0 point. We talked about the scaling granularity. We talked about potential per channel and group quantization. We talked about how to do the range clipping for the inputs. We talked about exponential moving average. We talked about minimizing the KL divergence, minimize the mean square error. We talked about the rounding. We talked about this round to nearest, as well as this ADA round. Okay, so that's pretty much all we want to cover for linear quantization. So next, I want to cover the last topic, which is the binary and ternary quantization. But before that, like this one, I think shows the comparison of different, different configuration. So let's take a look at the networks. We have GoogleNet, ResNet 152, MobileNet V1 and V2. For activation, and then you can see that all these linear quantization, they are all integer 8. And for activations, it's using symmetric linear quantization. It's the potensor. and it's used to minimize the KL divergence. For weight, it's using symmetric and the potential, and this is the performance. Okay, and if we are using asymmetric quantization and the potential EMA for for the activation and the inputs. For the weight, we are using symmetric and the per channel quantization, and you can see that the second configuration gives you better performance. This one has a zero accuracy drop. This one gives you but this one actually gives you a bigger accuracy drop. So different configuration will perform very differently on different networks. I guess that's the takeaway. Question mark, how should we improve the performance of quantized models? So that's what these quantization aware training is about. So far, what we have assumed is that we train a model with full precision, and then we just apply the linear quantization and see how good it performs, right? But apparently, anything we learned so far is that usually after the quantization and after the pruning, by doing a few rounds of fine tuning and the training, we can recover some of the accuracy loss, right? So that's similarly here. After we apply the linear quantization, can we what kind of training we need to do to recover some of the accuracy drop? So that's what the quantization aware training is about. So if a model is already quantized, can we recover some of the accuracy? So the idea of quantization aware training, this QAT, is that this is the k-mean base. This is the k-mean base. So to minimize the loss of accuracy, especially after aggressive quantization, fine-tune a pre-tuned floating point number provides a better accuracy than training from scratch. So the whole idea of this quantization aware training is this. So we retain for the model, we retain a copy of the full precision weights. Okay, and then therefore, then we have two copies of the weights. One is the original full precision copy. One is we apply the linear quantization already. Make sense? Two copies. And how do we do the training to recover the accuracy? The idea is this. So during the forward process, because training you have a forward and backward, right? During the forward process, we apply the linear quantization, whatever quantization we're using, be it k-mean based or linear quantization. So and then we are going to do the quantization and do the forward propagation. So we do both weight quantization and activation quantization. Finally, got output. So after you got output, you compare with the grounded truth and you do the back propagation, right? But when you are doing the back propagation, you got all those gradients, right? And the gradients are not added to the quantized model. The gradients now are added back to the full precision. Does that make sense? So I have two copies, right? Original copy and a quantized copy. During the forward process, I'm using quantized weights to calculate the result and calculate the loss. Okay, and after loss, do the back propagation. The gradient is applied back to the full precision. Okay, and by doing that, where's my? So this is so-called a simulated or fake quantization because we keep both copies, and the back propagation is not applied to the quantized weight. It's actually directly applied to the original precision. But if you think about it, there's one thing that we need to fix here. When we are doing the forward propagation, when we are doing the forward pass, we are using this fake quantization, and everything is calculate the input is calculated with the quantized weight, and the activation are also quantized, so you get the final loss, right? And then during then like when you are doing the back propagation, you need to go through propagate the gradient back to the quantization process, right? But the quantization is a discrete function. There's no gradient. Gradient is zero, right? So the gradient for the quantization function is zero. So therefore, the loss cannot propagate back to the model. Does that make sense? So what we did essentially, which is when you are doing the back propagation, you are going to skip all this quantization. You just pass them through the path, just using the quantization as an identity function, just itself. Okay, that's what we did in the back propagation process. So for the all these quantization function, we just treat them as an identity function, just pass the weights through back to this. And then like same here, when the gradient are passed back here, and you need to accumulate to the weight, right? The weight quantization also is a discrete function. So no way you can pass the gradient. So just skip it and apply back to the original weight. Okay. So in this way, we kind of tune the original weight. The whole purpose of doing this is that we hope to adjust the full precision weight so that it can tolerate this quantized inference, because all these losses we generate is because we did the quantization. Does that make sense? So by doing this, we gradually accumulate all these gradients back to the weight, to the full precision weights. And then like after we are done, now the new full precision weights, they already learned, they can tolerate this quantization error. Okay. And then like during the inference, we just get the quantized weight and do the inference. That's how we do this. So this is so-called this quantization aware. So you can see that. Well, if you are not doing this training to recover the accuracy, you can see the accuracy over here, and the quantization aware training can recover the training for mobile V1, V2. You can see it can recover the majority of it. Well, for example, like for this one, 0.1, you can recover back to 70%. For this symmetric, it's almost identical to the floating point. So 71.1, 73 to 73.9. Okay. So far, we learned about all this linear quantization. We learned about different ways of quantization. We learned about where to apply it, and how to clip the inputs, and how to after you quantize it, how to fine tune it to recover the accuracy. And you can see that after everything, with a integer 8 linear quantization, you can almost got pretty much the same accuracy as the original floating point 32-bit number, which is very impressive. So after this, the final topic I want to cover is this binary or ternary quantization. So basically this is trying to answer the question that, well, I can quantize a 32-bit floating point number to a 8-bit integer. Can I quantize this to 4 bits? Can I quantize this to 2 bits? And the extreme is 1 bit, right? Can I quantize a 32-bit number all the way to 1 bit, a binary weight? What will happen? Okay, where is the extreme? right? Because that's pretty much the limit, 1 bit, right? So let's see what's happening here. So binary, can we push the quantization position to 1 single bit? And that sounds crazy, right? And that you probably feel like, we get rid a lot of we just discard a lot of information by quantizing from a 32-bit number to back to 1 bit. But there are, smart ways to recover some of the accuracy, and that's what we are trying to learn here. Let's start from this example. So this like these are all integers, 8 next 3, 5 next 1, 5 2 0 1. Here I actually assume it's a real number. So and if we can quantize them to, if we can quantize the weights, if we can quantize the weights to binary, so 8 next 3, 5 next 1 becomes 1 next 1, 1 next 1. Okay, that sounds crazy. But apparently we lose a lot of accuracy, but the memory saving is significant. The computation, we also like save some of the computation. But the first question we need to answer is how do we do the binarization? For example, like here, is it like just positive number going to be 1, negative number going to -1? Is that it? Right. So that's one way to do the binarization. This binary connected paper, they propose 2 different binarization methods. One is this deterministic, basically says, if the number is greater than 0, then it's 1. If it's less than 0, it's -1. Okay. It also has this stochastic binarization, using a probability to determine, this number sometimes becomes -1. How likely this number should be 1, or how likely this number should be -1. But this one apparently it's harder to implement because you kind of like during the runtime you need a special hardware to generate random number to do the quantization. But nonetheless, let's take a look at what's the what will happen. So another method, another way of thinking to approach this binarization is that can we use the same idea as the linear quantization? Instead of just simply squash the whole number into 1 and -1, can we do some linear transformation as what we did with linear quantization, right? So the idea is this: instead of just just do this, can I using this binary weight times a scale, right? And if you want, you can also add a 0 point. But let's say like it's a symmetric quantization, and let's just adding a scale number. And then you got this. So these 2 different ways of doing the quantization. So we compare the reconstruction error. So weight minus the weight after the binarization, and the same here. So you can see with this linear transformation, the reconstruction error is a little bit smaller. But actually, if you look at the actual accuracy for AlexNet, if you just simply doing this binary connector method, you just 1 -1 thing. If you're adding this scale factor into this binary weight matrix, the accuracy drop. While actually this binary weight network actually even increased the accuracy by 0.2. And this binary connect has a accuracy loss of -21.2. The next question we want to answer is asking that, well, you just quantize the weight. Can we quantize the activation as well? What will happen? Okay. You have this, 5 2 0 1 now becomes 1 1 -1 1. Okay. What will happen? So this paper, this paper has a very interesting idea. Wow. So basically what it says is that for original, if we do this, 1 times 1 equals to 1, right? So 1 times -1 equals -1. -1 is 1, -1 is -1. Well, since we already quantized everything to binary space, we don't even need an integer adder or multiplication. We can just using bit operation, right? So instead of using this multiply number, I can just use an XNOR gate. Even better, right? Just one gate to do the calculation. Okay, and it's kind of smart because what you can see that it's a one-to-one mapping. So for now, like for ones, I'm using 1 to represent. For next one, I'm using 0 to represent because I can only represent 1 to 0, right? And then like for 1 times 1 equals 1, so I use an XNOR gate. 1 XNOR 1 give you 1. Okay. 1 times -1 give you -1, but 1 XNOR 0 give you 0. Okay, so you can see it's a one-to-one mapping. Okay, does that make sense? So we can perfectly use the XNOR to replace this multiplication hardware. So that essentially reduces like many gates in this adder just to one single gate. Okay, that efficiency improvement is huge, right? But the problem is if we plug this into the addition, now there's something wrong. If you look at the addition, so multiplication, there's no problem. But if you look at addition, so this is 1 plus -1 plus -1 plus -1 go give you -2, right? But if you are using the XNOR, give you 1, 0, 0, 0, give you 1. So -2 becomes 1. So it's not correct. So we can use XNOR to approximate multiplication, but we can't solve the addition problem, and that won't give you the correct answer. Make sense? So the XNOR net paper, again, they have a very interesting idea. What happens is that, well, he says, when you are adding these numbers together, I'm not going to do the add. I'm just going to do this the non-count. What happens is this. What they propose is this the pop count function. Says, well, if I can't get the correct answer, what I'm going to do is that I'm going to do some scaling first. -1 plus 2 times the original function. And then instead of adding these stuff together, I'm just going to count how many ones in this inside. And they prove that's equivalent to do the adding in the original equation. Okay, so in this way, by replacing the multiplication and addition with XNOR plus the pop count, they can reconstruct the output. So that's that. So this XNOR net paper basically says that, well, I'm going to replace the add and the multiplication with XNOR and the pop count. I can reduce the memory significantly. I can reduce the computation significantly. I think they have accuracy. Yes. Is this the accuracy? Yes. So you can see that. So the AlexNet, if we are using the linear transformation, the accuracy has a bit of pop actually. If you are using just the simple binary connected paper where the actual drop is this, the XNOR net, the actual accuracy drop is -12.4. It's still not as good as the linear transformation, but it's better than just simple binarization. So this one is doing this ternary network. So basically it says, well, instead of giving you 1 bit, now I'll give you 2 bits. What can you do? Right? So give you 2 bits quantization. What can you do? So with 2 bits, apparently you can represent, um, uh, 4 numbers. Okay, and that's that. So this paper, this ternary weighted network, essentially trying to show, how what are possible. So it gives you this example. Also, this one is doing this linear transformation, and it give you shows you this example. Well, if you just use 1 bit of linear transformation, it's 60.8% for ResNet 18, but for 2 bits, you can get, you can actually, the accuracy increase is quite significant, because with 1 bit to 2 bit, you can get accuracy of 65.3. Because the full precision is 69.6. Does that make sense? And then they also have this trained ternary quantization paper. So the idea is that, well, instead of just using the 2 bits to capture like from -2, -1, 1, and 2, instead of like using those two range, they figure out, well, -2 is not always the best number. I made the best solution, maybe I will quantize this 2 bits to use, for example, I'm going to use a 1, 1 to represent an 8. So with 2 bits, I can only represent 4 numbers, right? But these 4 numbers I can use to represent different numbers. I can represent like -8, -1, 1, 8. Does that make sense? Or I can represent -2, 1, 1, 8. So basically it's trying to learn what is that R number? What is that the 8 number that it can learn to give you the best accuracy. So they try to compare with all these ResNets, and they find out they can bump the accuracy even a bit more than the 2-bit ternary weight quantization. So that's binary and ternary. So that kind of answer us where is the limit? If we push everything to the limit, what's the best result? What's the best result we can do? Finally, just I think it's just 1 or 2 slides to talk about mixed precision quantization. So for all these different layers in this network, so far we assume once we determine the weight bit and the quantization bit for one layer, the second layer is going to be used the same. But end up different layers are different. They don't need to use the same number of bits for the activation and the weight and the activation. So, for example, this kind of non-uniform mixed precision quantization for different layers is the best solution. But how do you determine, what is the best weight and the activation quantization for each particular layer? So this paper essentially proposed this reinforcement learning-based method. The idea is very simple. So for every configuration, I have an actor. I'm going to train this model, get its accuracy, and critique it, see how good it is. Right. So that's and also they deploy this into the hardware and see how good they are. So this one compares the latency and accuracy. This where's the original baseline? I think that this is the baseline. The red one is the HAQ. Use this mixed precision. So you can see that and this blue line is this uniform quantization bits. And you can see that HAQ with the same latency, it will give you higher accuracy, or the same accuracy will give you lower latency. Well, at least compared with the uniform. They also tried on these different constraints. Because when you are doing the reinforcement learning, the reward function can be, I want to, have smaller size, I can have smaller latency, or I can have fewer energy consumed. So all they just plot different as different constraints here. One thing quite interesting that what they show here is that they tried this for for edge devices as well as the cloud server, and they find out that the algorithm, the reinforcement learning, will find different quantization bits for different requirements. Because for example, for cloud models, usually you want to maximize the throughput, right? But for edge devices, usually you want to minimize the latency for the edge devices. And they find out like when you are using different, the reinforcement learning model actually will learn that. For example, for this edge device, this model running on edge device, they find out, well, the early layers should give them higher bits, okay? And the later layers actually give you lower bits. But whereas the cloud model, the early layers, they are giving them fewer bits, and the later layers give them higher bits. And they just, once you input a constraint, they will automatically adjust different quantization bits for different layers. So that's the takeaway for this paper. All right, so that's all for today's lecture. Summarize, we talked about, it's quite a bit. We talk about k-mean quantization. While we briefly go through the number data types, we talk about k-mean quantization. We spend a good amount of time on linear quantization. We talk about all these different granularity, dynamic range clipping. We talk about rounding. We talk about this hardware quantization aware training. We answered the question, what happens when we are pushing everything to the limit? We quantize to 1 bit, to 2 bits, right? What kind of accuracy we can achieve. And then we talk about, how to automatically find the best quantization bits for different layers. Okay. Right. So that's all. Thank you. Yes.
Aware trading, is it still minimizing like the size?
So in quantization aware training,
since you still have to have the weights and the inputs without like
this, right?
minimizing the size, yeah.
So quantization aware training, the purpose is to recover accuracy.
Yes.
The quantization is just the linear quantization will apply, right? Whatever decision we made, we just put them here. The answer, the question we want to answer in this work is that how much accuracy we can bring back by doing some after quantization training, right? So the idea is that, well, I'm going to retain the original full precision weights for this original model.
Yeah.
Also, like I have this quantized weight, right? Okay. The quantized weight, because I did this weight quantization, I did this activation quantization, right? Then like during this training process, what I did is that in the forward process, I'm going to use all these quantized weights and a quantized activation. And I'm going to have a loss function to calculate loss, right? Okay. Now, originally, you would think like when I'm doing the back propagation, I should propagate it to the quantized weight, right? That's the I would think like I'm going to propagate the weight, the gradient back to the quantized weight. So what this work find out is that that's not the best way. The best way is the gradient are propagated back to the original full precision weights. Okay, and then quantize that back to the quantized weight.
Okay, I understand that. I guess where I'm confused is like how you actually deploy the model.
Oh, the model
onto a device. Is it still small enough to put on an edge device?
Yes. So
because this is just training.
Right? So after the training, the deployment is again, it's the quantized model. Yeah.
Okay.
This is just trying to do a couple of rounds of training to recover the accuracy. But the final deployment is still the linear quantized weights.
Okay, that makes sense. And Do you need the back propagation on the deployment, or is that just training phase?
Just the training base.
Okay.
Deployment is just some forward inference.
Yes. All right, that makes sense.
That makes,
Yeah, thank you.
yeah.
Okay,
Okay.
no, I think that was the same question.
Okay.
That's good.
Okay.
It's direct vote.
Sure, and I'm going to.